Welcome. Hello. So welcome back for the second part of your journey. I am Anthony Perrin, so I'm managing a partner alliance for South Europe. And managing partners and collaborating with partners is also a journey. So I want to thank Accenture, Sedona, Red Hat. We have also Zenica, and I want to thank all those partners, all those sponsors, and GFI for sure, for their support and engagement all during this year. And how rewarding it is when a partner positions Couchbase when performance requirements is at its peak. So fasten your seatbelts. I want to, from the grassland of Patagonia to the shore of Italy, I would like to introduce you, I'm proud to introduce you to Juan Manuel Ventura, Head of Architecture at Spindox. Thank you very much.
Thank you, everyone. So, yeah, it's all about performance and how we need to put together a system on which real-time is key for the Formula One industry. So, 2 words about Spindox. We are an Italian system integrator. Nowadays, we are almost 500 people. We have 5 offices in the territory and 3 branches abroad. We have a research and development hub in Trento, which is in Italy, and we like to think we are the strongest partner in the country of Couchbase. About me, I'm working on this industry for the last 10 years. Lately, I enjoy unpacking complex systems into manageable pieces, and this means distributing complex problems into smaller ones. I'm personally passionate about databases, and nowadays we as a company are focused on digital transformation as a whole and helping companies to leveraging their data free from technical constraints and creating engaging experiences. So the challenge was to handle a customer, which is, of course, I'm not supposed to talk about brands, but I think you already can imagine what's the customer. As a quite famous Italian car maker, which is obsessed about performance and security. So building a real-time solution for on-demand metrics and analytics able to scale from as little as running on a laptop to go to a whole data center. We should guarantee the availability and consistency of data while we should continuously ingesting information. We needed to make room for different data models, all by using a single technology. We didn't want to get too complex because the current solution is quite complex nowadays. And we needed to handle many different situations and exceptions about out-of-order data, replayability of events, data immutability, and these kind of troubles. The other key topic is about how we're using and how we needed to use a database on which for the application domain we are working in, we needed to be a very specific database, which is a time series on which there are many products filling this niche, but we needed to be done with a single database. So we teach Couchbase to do some time series paradigm. So we had two different goals. On phase one, we was supposed to overtake the current offline and testbed system, which is based on InfluxDB. InfluxDB is nowadays is like the de facto standard on time series databases. And on top of that, we needed to deploy and to implement several key features. As real-time data streaming, we needed the system not to block the streams and to push events directly from the server to the clients. We need also to do stream processing of this data. And we did so put in a rule engine, which is a module that can process this information in real time as soon as the data comes into the system. And we expose this as a programmatically interface for the customer, for the end user to program the system and to change behavior. And the most difficult part was to model Couchbase as a time series database, as a relational database, as an object database, all at once. And making use all of these key features as XDCR, nickel, memory first architecture, and so on. For phase two, we need to apply this technology to replace the current telemetry system. And the figures are quite important because we have to handle more than 30,000 channels, plus calculate many virtual channels, which are the metrics of the race car that are coming into the system. We need to handle sample data coming from 1 hertz to 100 kilohertz, which is 100,000 times a second. We need to handle full nanoseconds resolution. We are at the demo I'm going to show you later on is limited only to the millisecond. And we need to work locally, so at the place on which the race is having place, and stream data directly to the headquarters in Italy. And we are using a combination of application level streaming for the real-time but ephemeral data stream, and we are using XDCR for a delayed but persisted data stream. So what we need from Couchbase and why we choose Couchbase for this task? Well, we needed to support high performance, asymmetrical scalability, so the chance to scale the system differently, maybe by splitting services, indexing data and query, high availability, and we needed to have some sort of mechanism for replication, which is distributed again, and of course, low cost of operation. We needed to have an in-memory grid database, so we're using this key feature of Couchbase, being that thanks to its memory-first architecture. And we needed to support different data models. So time series again, for data points, we're using maps for doing so. Object models of document database for metadata and master data. And many relational data, which was expressed thanks to the flexibility of the JSON's capabilities. And we needed different data access patterns from a single database. So we are using a mix. We are using key value for fast access data in a way that we can determine the key even from the front end without any trip to the server. We are using nickel for querying the metadata and master data. We are using MapReduce for aggregating for the X in nanoseconds, milliseconds, microseconds, and whatever. And the Y one, so we are using some aggregation function as well. And we're using full text search for everything that's not a numerical value, so log messages and this kind of data. And this is the solution. So this is Argus, is the system we built with these technologies. In Argus, everything is seen and treated as a stream of events. An event is just a value observed by the system at a certain point in time. So it has the x-axis and the y, which is the value. A sequence of these events makes what it's called a series, and this is the thing that we observe using this system. And both the real-time data and the historical data are meshed together into a single stream using a combination of key value and nickel queries. Another very important thing is that we put together some strategies for segregating data by the access pattern, using different buckets and indexes. So for master data and series, which is the metadata, we are using global secondary index and nickel queries for querying this information. The events, which are let's say, the transactions of the system, are stored and accessed by a key value pattern, and they are calculated in the deterministically way. And we have log messages, and every text message is implemented like in a different bucket using full text search indexing. So basically, the whole system works on a two-step operation. So any client, in order to consume data, I mean any client because the system is absolutely modular. You can ditch the HTML5 dashboard, and you can plug anything else. And we are developing in parallel different clients. So it's reduced to two operations. One, you have to isolate the series you want to work with. So using a combination of nickel and the hash calculation that you can do even on the front end. And then once you have your series, which are just the hashes, you can subscribe to that events from Argus, and you will have your data pushed by the server, or you can query historical data on demand. So basically, the architecture is, Argus is a reactive distributed system based on the microservices pattern. For the sake of this demo, I'm going to show you just a reduced version of this. The communication between modules is handled by a message passing pattern, which implements just two different communication patterns. Request reply for commands, which are blocking, synchronous, and command-based, and the event emitter pattern, which is non-blocking, asynchronous, and fire and forget as a strategy. And the whole system is to be seen as even event-driven, because every microservice emits and subscribes to events on which reacts through functions, signals, and data packets. So the thing is, all the logic is put into the single modules. Every module is very specific on what they do. And they communicate with each other, just passing around data, just data. At every step, of course, this data is enriched, is evaluated, is processed, is handled. And every module reacts to this data independently and in real time. This is the high-level diagram. Again, we are just seeing a simplified version of the architecture because most of it is confidential. But basically, all the data is coming from sources. The customer is not using this just for monitoring the car at the event of the race. They are using this for simulating races on the laps, and they are plugging into the system even historical data to the system. It doesn't care where the data come from. It is able to process it anyway. So everything starts at the collector, on which gets all the raw data. As soon as it comes to the system, it gets bounced in everything, in every other module, and at every step it gets analyzed and processed until it gets away out of the system again through the dashboard. So what we are going to see is a demo of the real thing. Okay, this is Argus. This is working in real time. As you can see, everything is moving. The x-axis is already synchronized, so the time is common for all the charts. We can select different dashboards. We can move around along the time frame. Everything that you are seeing is actual data. Is a development environment, but anyway, it's actual data. The zooming, as you can see, is very snappy. Is because we have this performance thanks to the key value access pattern. So every time the dashboard asks for data, it knows exactly the key of the document they need. Okay, in this case, we are changing strategy, and for determine what's the series we need to subscribe to, we're using nickel. So what you're seeing now is a user interface that is absolutely built and thought around the customer experience, but behind the scenes is just writing a nickel query, which is the only thing the system needs to subscribe to this series. Once it has the series, data is coming to the dashboard, flowing from the server. We have another killer feature, which is the variables. So we are defining here variables that are used by the client for interpolate these values. And again, aiming just to get the series hashes. So in this case, we are seeing that we are just defining hard-coded values into this that they are used to find out what are the corresponding series. So again, we're just filling all our fields, but in this case, we're going to use that variable, which is interpolated. And again, the system is going to get all the series that match these criteria. So in this case, we only have 3 for the sake of this demo. Okay, now we are going to define another template variable, but this time we are issuing a nickel query directly to the system. So the same thing, but instead of hard coding our values, we are just writing a raw nickel query. And as you can see, the only thing that we aim for is to get the series hashes. Okay? Great, and now we are going to use this. Again, we are just defining a single criteria, and the system are going to interpolate everything that match this query on the server. So we only need to do it once. Okay. And again. Okay, this is the core of the system. We have this rule engine, which is the way we can change the behavior of the system when the system is running. So we don't need any deployment for creating new kind of business rules. So we are selecting the series on which we want to work. And here we define our rules. The rules are used to calculate virtual channels, to alerting purposes, and to extend the system behavior. So in this case, we are only raising an alarm. We can, as you can see on the action select, we have many different plugins in place, so we can run a process, a script, call a web service, or do basically whatever we want at the presence of when the criteria is met. So in this case, we are just raising an alarm, and we will see now that as soon as an event satisfies this rule, the alarm is raised. Okay. And this is, again, at the core of the system. This is the entry point on which we are receiving, this is, again, in real time. We are receiving data, and we have implemented these on different, excuse me. Okay. In this case, we have implemented different protocols, and the system, once more, is extendable because we have many built-in protocols for ingesting data, which is the most stressing part for Couchbase, because the thing is we should keep the service level while we are ingesting many amounts of data. So in this case, what you are seeing now behind is the influx interface, which is just a protocol because the customer already had this solution. But we have plugins for StatsD, Snap, and many others. So this is real time again. And what you are going to see now is some figures for Couchbase. So we have different buckets for different functional boundaries. These are real data, so we have this kind of stress on the system. This is just a test. Dev environment on production is much bigger. And as you can see, on points, we have most of the data. These are the points. These are the real data. The rest are just metadata. In this case, we are handling everything with just 3 nodes. And this is more or less what's the system load at the moment. So we have peaks of, we are going beyond 10,000 operations per second. And everything is perfectly fine using just an average of 20% of system load. So the benefits. So we have completely decoupled the system and use a general purpose database model as a time series one, and with even not losing flexibility to express relations and objects using the Couchbase. From the performance point of view, we have, this is preliminary data, but we have peaks of an order of magnitude more performance than InfluxDB. This is on reads because InfluxDB is a nice product, but is quite specific. So you cannot use influx for storing your master data. And the version of SQL-like query language is quite limited. So the benefit was to replace influx with Couchbase by using Nickel. And the other key feature is to use XDCR for replacing is the influx relay, which is a technology for replication, which is quite limited as well. So XDCR is much more robust. Okay. Well, what's next? We didn't do yet any optimizations for performance, and we already have this performance which are quite good. We are nowadays working on a Grafana plugin. Grafana is just an offline HTML dashboard. So we are writing a plugin in order to connect Argus, which is perfectly decoupled from the front end with Grafana. Argus now is internally becoming a platform because we are accommodating more and more functionality, not necessarily for time series domain. And we are using the platform for different application domains, medical trials, business events, and for IoT, we are using for other telemetry system, preventive and predictive maintenance as well. So, what we have learned building this system? Well, first and foremost, building this kind of distributed system are really hard. Specifically, modeling data is key, and it was the hardest part. It took 3 months to make it, to get it right, to model the whole thing. Replayability is key again in order not to have the complexity of guaranteed delivery in a message system. Impotency as well, instead of using exactly once delivery. This is very difficult and very hard to get, and very hard in terms of performance. And commutativity instead of order delivery, which is, again, at the center of this problem we have to solve, because data can come at any moment, and we cannot control this. And, of course, using the right tool for the job. In this case, again, Couchbase was the right choice because we have so many different approaches and different technologies all on this on one package. So we're using a mix of key value, Nickel, full text search, and MapReduce all together for the right use case. Okay, thanks.